Okay, let's get started with the second talk of the afternoon. The speaker will be Blais, who's going to tell us about the analysis of partially symmetric functions.
Favorite problems and conjectures and property testing. And also along the way, I want to talk about the connection to partially symmetric functions. So there might be many different ways we can define what we mean by partially symmetric functions. So the way I'm going to define it, I'm going to try to convince you is natural and a nice way to think about it. So to do this, I'll start with a simple exercise. Pick your favorite complexity measure, whether computational complexity, learning, testing, anything you want. Now think of the simplest functions that, according to this complexity measure. I'm willing to bet that whatever you've thought of, constant functions will have the lowest complexity measure. Okay, so that's not very interesting. If I were a bit more adventurous, I would guess that juntas also have very low complexity under whatever you're thinking. So when we think of simple functions, especially in this room here or in this workshop this semester, juntas often come to mind. Something that would be more risky and really depends on what you're thinking of is I might say that symmetric functions are simple. So for many complexity measures, symmetric functions do have small complexity. For others, that's not true at all. But now this is kind of the picture I want to think about for now. We have these constant functions and two bigger classes of functions that are still simple in many settings. And the question is there something that we can define that actually encompasses both of these classes of functions? And this is what we're going to call partially symmetric functions. And more specifically, the way I kind of want to do this, I want to think of partially symmetric functions as the analog of juntas for constant functions. So what is a junta? One way to think about it is that it's an almost constant function. There's only k variables somewhere, k coordinates, that as long as you fix them, then the function you get is constant, no matter what values you get. The juntas? So
they're presumably, once you fix the k, then it's symmetric.
So for the juntas, if you fix the k, you get constant. And then we want the same thing, where if you fix the k, you get something that's symmetric instead of constant. And this is how we can define this. We can say f is n minus k symmetric if there's a set of k special variables where exactly this happens. Or another way to say this, if any two inputs that agree on those k variables and have the same Hamming weight on the rest of the variables, they have the same value under f. I'm going to call these partially symmetric when k is a constant. You might look at that and you might say this is very nice from a computer science point of view, but let's think about things in a more algebraic point of view. We're talking about symmetry here, so here's another way we might approach the problem of defining partial symmetry. We might say permutations on the set from 1 through n define actions on Boolean functions by just relabeling the input variables. And so we can now look at a given function at the set of functions we obtain under every possible relabeling of the input variables. And we'll call this the isomorphism class for f. And now if our original function f was perfectly symmetric, then we still only have a single function. Any relabeling doesn't change anything. So we might want to say, okay, this is great. Let's call a function almost symmetric or polysymmetric if the number of functions we get is not necessarily 1, but is fairly small. And the parameter that ends up being nice for this definition is to say if the number of distinct functions you end up with is polynomial in n. And this is comparing against n factorial, which is the largest number possible. So we're talking about much, much, much smaller. Now what's interesting here, and perhaps another vote of confidence for the definition of partial symmetry that we saw before, is that if you start with this definition of polysymmetric, you really are studying partially symmetric functions as we defined them in the previous slide in hiding. Specifically, your function f is polysymmetric if and only if it is n minus k symmetric for a constant, so if it's partially symmetric. Okay, so this is a nice definition. What I want to do is I want to show you that it also shows up in computer science in fairly natural settings. I'll give you 3 examples of that, the last one being the one that I really care about and which will lead to the open problem. And then the second part of this talk, I'll kind of review some of the tools that we have to analyze these partially symmetric functions and where we might want to extend those tools to actually prove or get answers to these open questions. But now let's start with, okay, where do we see partially symmetric functions? It turns out we've seen them in computer science for a very long time. The first occurrence of them are in the classic paper of Claude Shannon on the circuit complexity of Boolean functions. This is the paper where he showed almost all Boolean functions have exponential circuit complexity, so 2 to the n over n. Now, this was the first part of the paper where he proves this lower bound. In the second part, he kind of says, this doesn't really make much sense empirically because on a day-to-day basis, all the functions I see have much smaller circuit complexity. Why is that? And the first thing he points out, which was actually based on earlier work, is that, well, oftentimes it's because the functions we try to implement are symmetric. And if your function is symmetric, you don't have exponential circuit complexity. You have only n squared is enough. And then he also gave a universal upper bound that applied to all Boolean functions. And this universal upper bound immediately gives you a constant size upper bound if you're a junta on a constant number of variables. So we saw these two classes of simple functions are simple in this circuit complexity model. The natural question to ask, and the question that Claude Shannon asked, is what about partially symmetric functions? And indeed, those are also very simple. And this is not very hard to show. Once you have those two results in hand, you can actually combine the circuits for juntas and for symmetric functions in a nice way to get a polynomial in n, again, upper bound for constant k, or even for small enough k. This result he did not even state, no. So this one it follows from his universal upper bound. Yeah, slightly disappointing, but it was too easy at that time for this result only. Let me mention one other example. Another thing we can say in terms of the circuit complexity of partially symmetric functions is that if you're partially symmetric, you can be computed with a constant depth threshold circuit. So the function is in TC0. And this was a theorem and not an observation of Clote and Kronakis, but only because they were interested in the polysymmetric definition that we saw. So most of their work really involved just trying to show that if you're polysymmetric, you're partially symmetric. And once you have this partially symmetric, again, this result, just like in the circuit complexity, is very easy to see. You can play around with it and get it. Another reason I wanted to mention this beyond the parallel is just because it's actually very interesting. It has other connections to other fields, including proof complexity, which I don't know here, so I'm putting in quotes what I think is the main result here. But from what I understand, Petassi and Santanan had this new model of effectively P simulations for proof systems. And they had this conjecture that maybe it has these nice results, like that Frege could simulate extended Frege under this new system that they introduced. But using this theorem, they could actually show limitations on the simulation model that shows that actually probably this conjecture that they were hoping for is false. So again, this it's exactly partially symmetric functions that show up in this setting as well. Okay, and now the star of the show is this testing function isomorphism problem. Let's take this very basic problem that I'm going to give you. I'm going to give you a truth table for some function f. And I'm going to give you a black box that computes some function g. Now, for starters, let's say that the question marks are filled in, that I've labeled the input wires. And now I ask you if g computes f. And I'm even going to make your life easier in the standard property testing sense that Ryan alluded to earlier. I'm going to promise you that either g computes f perfectly, or that it's completely off. It makes errors on a constant fraction of the inputs. If you have these input labels on the wires, this task is really easy. You just query random inputs and check against the table to make sure that you get the right value. As soon as I take away those labels on the input wires, this problem becomes very interesting. Now you're asking the question of whether there is some labeling of these input wires that I can choose where the function g computes f, or whether any labeling that I choose, I still end up far from the function f. And now the question of how would you test this black box g against the known function f becomes more subtle. It's unclear what exactly you would want to do, and in fact, it will depend on what the function f is. If I want to write this definition in words, the exact same problem that I stated here, I'm going to say we're going to define a tester that makes Q queries to be some randomized algorithm that has access to some function g, and it knows some function f, and in particular, it knows the list of all the functions that are isomorphic to f. And it just has to distinguish with high probability between the cases when G is actually isomorphic to F, or when G is far from all the functions that are isomorphic to F. And the main question, the question I really like, is can you tell me which functions for which I can test isomorphism with a constant number of queries, a number of queries that does not depend on n? And in particular, maybe I want to dwell on this just a second. Why do I like this question? The real question I'd really like to answer is not just for isomorphism testing against a given function, but for all properties of Boolean functions. And in my mind, properties of Boolean functions are just properties that are closed under relabeling of the input variables. And in this sense, we can think of these isomorphism problems as the smallest properties that are closed under this sense. And if we can solve this main question, I feel we'll have made a lot of progress towards this general question. So now that maybe I should, this really is the question I want to sell you on, so I should stop and ask if there's any questions at this point. Okay, let me. Great question. That's exactly what I was hoping for. Yeah, so we have these two simple classes of functions. So let's ask if we can test isomorphism against them. The first one are the symmetric functions. Actually, here, we're back to the function identity testing problem, because it doesn't matter what input labels you put on the wires in the original black box problem. So that's trivially easy. We can test isomorphism against them. And then a non-trivial result is that you can also test isomorphism against juntas with a constant number of queries. And the fact that this is a constant number of queries was due to Fisher, Kindler, Ron Safra, and Samorodnitsky, who also proposed this function isomorphism testing problem for the first time, I believe. But okay, so we have symmetric functions, we have juntas. Do we also have partially symmetric functions? Yes, this is a result obtained with Amit Weinstein and Yuichi Yoshida last year, and in parallel work independently by Chakraborty, Fisher, Garcia, Soriano, and Matzlia. If you're partially symmetric, we can test isomorphism to this function with a constant number of queries. What's really nice about this, the other applications or the appearances of partially symmetric functions before that we saw, the proofs that they were simple they were easy proofs. They were not particularly interesting proofs. This, on the other hand, turns out to be more technically interesting. So there are nice things that come up, and we actually need to understand a bit more what it means to be partially symmetric in order to prove this result. I have the main theorem that gives the main technical theorem that lets us prove this as the last thing for this presentation, if we have time. But before we jump to that, I kind of want to ask, okay, what's the next step? We have partially symmetric functions. Let's move on. Let's get something even bigger that includes everything. The punchline, we couldn't find anything. We do not think that there is anything, essentially. So we think we have this conjecture. And again, these two papers that were done independently both came up with the same conjecture, that we believe any function that's far from partially symmetric is hard to do isomorphism testing against. And here I put log k, but really what I mean is it's a function that's going to grow with k. So if you're not close to partially symmetric on a constant number of variables. Well, so it's going to be a function of k, but I kind of want to say either you're going to be close to n minus k symmetric for k constant, or far for something slightly super constant.
Why the log?
Oh, that's arbitrary.
What?
Because I was not brave enough to put k in here.
I don't have any specific reason.
No. I wanted to write little omega of 1 as a function of k, but yeah, this is really what I mean. I want to say that this will grow as a function of k. That's the real conjecture. No. Okay, so why does it have to be k and n? I can have a partially symmetric functions on 3 variables. That's going to be far from being for k equals 3, which is far from every n minus 2 symmetric function. Very far from it. So in this case, yeah, so this might not be the best statement. But the punchline is that yes, if you're really not partially symmetric, there should be an n dependency on the query complexity. The second part of the talk is kind of explains why I'm talking about this here. I kind of think that the tools we have here and that we love exploring are the tools that we need to prove this conjecture. And just to give you a quick overview, we do have some connections to influence and to some of the other tools that we know and love. And I'm just going to quickly run through what these tools look like, what we do know. The first thing that we know is that if you take the usual notion of influence and of total influence, and perhaps this not as standard definition of the influence of a set of variables, which is just the probability that you flip the value of the function if you re-randomize all the bits in this set. If you look at these three notions of influence and you ask, can we do the same thing that measures not influence in terms of where this notion of influence is really used for juntas and constant functions, can we do something similar for symmetry and partially symmetric functions? And we can. And the right way to do this is, instead of looking at the influence of a single variable by flipping that variable, now we want to ask about the symmetric influence of a pair of variables, I and j, which is just the probability that you flip the value of the function by interchanging the values of xi and xj. You can define total influence in the same way as before by just summing up the individual influences. And we can do, again, the influence of a set of coordinates by just saying now, instead of re-randomizing each bit in this set S, we're just going to permute them uniformly at random. Okay, so if we define these tools, do they help us? Can we say anything interesting about them? We can, and we can even visualize what they look like. Really, they're measuring the number of bichromatic edges on a graph that corresponds to the function. It's just a different graph, where now 2 points are connected if they're related by just a transposition, instead of just flipping coordinates. But let's look at some facts. Okay, some easy facts. If your function is symmetric, the symmetric influence is 0, which is what we would like. We can represent the influence of a pair of coordinates in terms of Fourier coefficients of the function, which is nice. And we can even prove some really nice theorems, like what was mentioned this morning, Ryan and Carl's result, that we can prove KKL for this symmetric influence. Where now, instead of saying that f is balanced, we're saying if f is far from symmetric, then we do have a pair of coordinates where the influence of this pair of coordinates is large, is log n over n. And then for the testing problem that I mentioned earlier, it turns out what might be even more relevant is the other notion of influence of a set of variables. And here again, we can say some non-trivial and slightly interesting things. So again, we have this nice result that, nice, obvious, but this is what we want, that if you're n minus k symmetric, it does mean that you have a set of size k where if you look at the symmetric influence of the remaining coordinates, it's 0. We have, again, this Fourier representation of the symmetric influence. And we have these two facts that mirror the same facts that we have with the standard notion of influence. The first one is that the symmetric influence is monotone. If you add the number of coordinates that you consider in your set, you can only increase the symmetric influence. It doesn't go down. Subadditivity is something that holds for standard influence, where now if you look at the union of two sets, you look at its influence, it's bounded above by the sum of the influences of the sets. This is no longer true with this notion of symmetric influence, but it's almost true in the sense that if your sets are large enough, the symmetric influence of the union of the sets is almost bounded up to some factor that depends on the size of the sets by the sum of their symmetric influences. And what we'll see is that we can actually use this to prove the upper bound result, to prove that partially symmetric functions are isomorphism testable. And this is actually the one main result that I want to talk about, the one that implies the theorem that we can test these functions efficiently. And what it is essentially a robust version of the first fact that we saw. The first fact that we saw is that if you're n minus k symmetric, there's a size k set where the remaining influences have the remaining coordinates have influence 0. There's the converse. If you're epsilon far from partially symmetric, you can, for any set that you identify, the remaining coordinates will have symmetric influence at least epsilon. And what this theorem says is that we can say something even stronger. So now, instead of just picking a small set of size k and looking at the symmetric influence of the remaining coordinates, I'm going to say, let's be sloppy. Let's just partition all the coordinates into k squared different buckets. And now, instead of picking k coordinates, I'm going to let you pick k buckets so that you can try to minimize the symmetric influence of the remaining guys. And no matter how, if we pick this partition at random, no matter how you choose these k parts, the remaining coordinates will still have influence, symmetric influence that's linear in epsilon, so still very large. Now, the reason I mentioned the proof here, really the main message I want to bring is that we couldn't prove this with Fourier analysis. The analogous statement for juntas is a Fourier, it's a simple proof using Fourier analysis. And when we started this project, we just really wanted to have the same proof. We couldn't make it work. This would be one of the challenges. So already for the problem session, it would be great to have a proof of this theorem that just uses Fourier analysis. But the proof that we got used instead a surprising connection with intersecting families. And so I'm going to run through this proof. This proof has essentially 3 arguments that I'm going to make. And if I can back them up, then the theorem follows. And the main idea of the proof is just to say, let's look at all the sets that could be bad for us. Let's look at all the sets where if I chose that set, the remaining coordinates have very small symmetric influence. And very small at first will be epsilon over 3. The first claim that I'll back up in a second is that this is just not any set. This set has to be k plus 1 intersecting. Any 2 sets in that family must have intersection size at least k plus 1. Now, once I've done that, we're actually almost done. Because then I'll say there's 2 possibilities. Either this set has, this family has a small set inside of it, in which case I'll give you another simple argument to show that this means that with very high probability, any k parts will satisfy this condition that the remaining coordinates have very large symmetric influence. And on the other hand, if there's no small set, then I can actually kind of boost this by looking at the family of even worse sets whose complements have even smaller influence, and I get a larger guarantee on the intersection size. And the reason I want to do this is because now I'm going to bring in the intersection theorem, originally of Al-Suede and Khachatryan, but we're going to use the Dinner and Safra version, which says that now if you pick a random set with some p bias, the probability that you end up in this family is going to be extremely small, p to the intersection size. So let me just quickly show you why these should be true, and then this will give you the proof. The first statement, why are the bad sets an intersecting family, is essentially just because of subadditivity. Take any 2 sets that you have, look at their intersection size. Now, we can use De Morgan if I did it correctly, and then subadditivity with some factor for the fact that subadditivity doesn't hold exactly. But we get the bound that this influence of the coordinates outside of the intersection is less than epsilon. But the only way this can be, because f is far from n minus k symmetric, is if that intersection has size bigger than k. Otherwise, I could choose that set to be the set of core coordinates in the n minus k symmetric function that's really close to f. So this gives me the intersection. The second argument is the easiest one that says that if you have a small set and you have a partition into enough parts, this set is going to be split. It's going to be shattered. Each element in the set S will go to a different part. But now, any way that you pick a union of j parts, you're going to have intersection size at most k with this set. We just argued that it's k plus 1 intersecting. All the bad sets have pairwise intersection at least k plus 1, which means that j cannot be a bad set. So again, the conclusion holds. And then this final step, the first part of it is exactly the same argument we used in step 1. And the last step is just the observation that if I fix any k parts, say you take the first k parts of the partition that you're going to get before you do the random partition, and you ask, what does this set look like? It's just a random set. And the density is going to be exactly k over the number of parts that I have, k over k squared. It's a random 1 over k biased set. And so now we apply this intersection theorem to say the probability that it's in this family that has very large intersection size is going to be extremely small, so small that we can actually apply now the union bound over all potential ways to choose k of the k-squared parts. And this is the proof. But again, the main message here was really just, can we do this with Fourier analysis instead?
Why do you want to?
Essentially, because I would like to understand how these tools help us understand partially symmetric functions better. So, right, a Fourier analysis proof by itself does not give us anything more, but I am hoping it brings us closer to resolving the conjecture. In fact, let me just close with some open problems here. Just some obvious open problems. The first one is, even if you don't like function isomorphism testing, I hope I've kind of convinced you at least a little bit that partially symmetric functions are kind of nice. They're a natural class of functions. It would be great to understand them better. Are there any results that we can have over regular functions that we can get analogs when we look at partial symmetry? So, for example, again, this morning we saw this already as an open problem suggested. Can we get a Friedgut-Hunter theorem over non-product domains? This is a very nice natural non-product domain. It does have a very natural notion of what it means to be a Hunter. It's just partially symmetric. Can we prove Friedgut's Hunter theorem in this case? We have a lot of results on the structure of the Fourier spectrum of...
Is there a particular conjecture?
If I were bold, I would make that conjecture. But to be honest, I just thought of this yesterday. It just hit me yesterday that, yeah, as far as I know, we don't even know this for this partial symmetry.
So here the influence will be influence so that you swap two guys at random and you say that if the sum of these influences is small, then you're close to a...
Partially symmetric, yeah. That should be, that seems like a reasonable conjecture that
So
at
we
least...
can make it. We can name this conjecture after you.
If it's true, I'll happily accept, yeah. Or I'll try to disprove it very quickly if it's obviously false. Yeah, so, I mean, one of the reasons I mentioned it also, I hesitated to mentioning this because I was thinking it might actually be known, and this would be embarrassing. But on the plus side, I would definitely know after this talk. Someone here would know if this is known. So if there is anything like that, that would be great. Yeah, the structure of the Fourier spectrum. We have lots of things for symmetric functions. We have lots of things for Huntas. What can we say about partially symmetric functions that's non-trivial and potentially interesting? And, you know, my motivation for this is, can we actually use these tools that we develop, or even the ones we already have, to actually settle this conjecture about function isomorphism testing? And then the other, you know, the general question is this a more general phenomenon? Do partially symmetric functions actually occur in other areas where we just haven't really realized it? And I guess the natural place to look at would be places where, you know, symmetric functions and Huntas do have low complexity under whatever measure we're looking at. And it's already been used in a couple settings. So I just want to mention local reconstruction, and this alternative model of property testing, or these different models where partially symmetric functions were actually a natural class of functions that showed a separation between 4 different testing models, where you allow more and more power, and you get strictly fewer queries needed in each model. And so that's it. This is what I wanted to talk about.
Any other questions for Ed?
Are there lower bounds for k log k upper bound for testing partial symmetry?
That's a good question. There might be a k lower bound, but I'm not sure right now.
And for Huntas?
For Huntas, there is the k lower bound. So testing isomorphism to Huntas is between k and k log k.
I see.
Just a comment. Partially symmetric functions also appear in they try to do lower bounds for symmetric linear programs. So
This is great.
the
That's
Inapproximability deals with has partially symmetric functions.
excellent.
And, when we try to put lower bounds in symmetric, it'll be short.
Excellent. We have to talk more about that.
Okay, so you mentioned the problem of recognizing when two functions are isomorphic.
Yeah.
You can ask a weaker form of equivalence where you don't just permute the variables, but you apply some linear transformation.
Yes.
Is there some work on recognizing when two functions are?
Yes.
Is this,
That's a great question, and it has been studied very recently, including by Carl. So this is like testing under linear transformations, and it ends up. That's a great question, in part because it ends up being more. It appears to be more tractable. We appear to be making more progress on that. The specific results they have. I mean, you should probably step in, but they have results showing that for some functions you have very strong lower bounds on how many queries you need. So you can give a universal upper bound and they give matching lower bounds. I don't know if there's work on, is there work on characterizing the set of functions?
We have something that's kind of similar, and sort of at a similar state, that we want to show that if you're epsilon far from having, say, small spectral norm, then it's hard to test isomorphism. We do have, in the general case though, I mean, there's a very naive n-squared tester for this problem, because there's just like there's a naive n log n tester for permutation isomorphism. We also have a lower bound of constant times n-squared many queries. And this is, but you cannot test linear isomorphism to the inner product mod2 function with less than constant times n-squared many queries. So in like the extreme case, like the linear isomorphism problem is resolved.
Okay, the same